We start the study of complex sampling by looking at the most simple design in terms of samples, which is called the simple random sample. For this topic, you should be reading Chapter 3 of the book Sampling of Populations by Levy and Lemshaw. So a simple random sample is defined as a procedure where everyone in the population has the same probability of being selected for a sample. And this probability is given by the size of the sample, in this case little n, divided by the size of the population, big N. Although this is not part of the curriculum of the unit, if you're interested in the details about the derivation of this probability, you can follow the link to a different video where I explain how you get this probability. A useful way of thinking about sample schemes is to consider the weight that each individual in the sample represents in terms of population. And this weight is given by 1 over the probability of each subject being selected for a sample. As we said before, in the case of a simple random sample, this probability that is given by the sample size little n divided by the size of the population capital N will correspond the weight of capital N over sample size. So if we consider a population of 1,000 individuals, and the most extreme case where we have a sample size of just one single individual, this individual is representing the entire population, so it will have a weight of 1,000. In a situation where we have a sample size of 2, because we are in a simple random sample scheme, each one of the individuals in the sample will represent half of the population, so it will have a weight of 500. More generally, for a sample of size little n, each individual in the sample will have a weight of capital N divided by small n. These weights are useful to derive estimators for population parameters. Throughout this module, we'll be focusing on 3 population parameters: the mean, the sum or total, and proportions, and the respective standard errors. I'm going to use the mean to motivate the derivation of these estimators. So let's suppose that we want to estimate the population mean of a certain variable x. We know the expression for the population mean is given by summing every individual in the population, that is going to be represented by x star, divided by the size of the population. Now, to use the sample to estimate the population mean, we will replace each individual in the population by the individuals in the sample weighted by the respective weight. So this sum in the population will be replaced by the sum in the sample. And notice that we are summing here over everyone in the population, and in the formula below we're summing over everyone in the sample. So if we simplify this expression, we get the known estimator for the population mean, which is just the sample mean. An estimator of a population parameter has an error associated with it, which is usually represented by the standard error, in this case the standard error of the mean. You might recall from other units that the standard error is given by the square root of the variance divided by the sample size. However, this formula is derived for large populations or infinite populations. For finite populations, it's better to use this formula. The extra term in the standard error appears from the finite population correction of the variance estimator. Although this is not part of the unit syllabus, if you're interested in the derivation of this finite population correction parameter, you can follow the link to a video where I give you the mathematical details. Knowing the standard error of the mean, it allows us now to compute the 95% confidence interval that is given by the formula sample mean plus minus 2 times the standard error. The term 2 times standard error, it's also known as bound error of the estimator or the margin of error. More generally, a confidence interval with any level of confidence is given by the formula on the right, where z1 minus alpha over 2 is obtained from the normal distribution. In the book you can find details about other estimators such as the sum and the proportion with the standard errors and the respective confidence intervals. To finalize, I would just like to guide you through an example of an hypothetical survey conducted among health professionals in a hospital where 200 staff members were randomly selected from a total of 2,000 employees. We are interested in estimating the mean age of the staff. So the file servhosp_age.csv can be found in the dataset folder of the e-learning website. I give you both the code for Stata and SAS. So we start in Stata by reading the data, importing the file CSV. Then we generate an integer that is going to be the size of the population, and another variable WT corresponding to the weight of each individual. Because this is a random sample, each individual is going to have the same weight that is going to be given by the population size divided by the sample size, so 2000 divided by 200. Now the next command, SVI set, will tell Stata that we have a complex design, and the FPC option is an option to use the finite population correction. So this SVI set will basically define the sampling scheme in Stata. So now we can compute the mean for the variable age, but we're going, instead of using the usual command just mean age, we're going to add the SVI that will ask Stata to use the sampling scheme. So in this case, the mean age is about 45 years old, and Stata also gives you the standard error and confidence interval for the mean. Notice that because this is a simple random sample, if we don't use the sampling scheme, you should get a very similar result. The only difference is in the standard error that is going to be slightly different in this case because we are using a finite population correction. And if you only use the command mean, Stata is not going to use finite population correction, so it's going to use the usual formula for the standard error. And finally, the SAS code for estimating also the mean of the age. And you can see again that result is the same as in Stata. And if you just run a proc means, you're going to have a similar result where the only difference that you'll find is going to be in the standard error, again because of the finite population correction. So be sure to complete the suggested exercises and go through the solutions. Good luck.